I will talk about integration today. And this lecture is especially for those students who are having difficulty in understanding the concept of integration. So I will start from the very elementary level to make you understand the concept of integration. So let's start the lecture. Here I have a rectangle. And if I ask you what is the area of a rectangle, you already know it is the multiplication of length and width, which is here A cross B. This is the area of this whole, and you are very well familiar with that one, right? Similarly, you know what is the area of a square. You know, a square is a shape in which length and width is equal. That is why this is the area A cross A. It is actually a simpler case of rectangle, because in the rectangle length and width are different. So we write A cross B. In the square we know length and width are equal, so A cross A, or we can write them A squared. You must also know that what is the area of a triangle. And we know that area of a triangle is 1 by 2, then length of the base, and then length of the height, where height is this perpendicular from top to bottom. This is h, this is b, and this is area of a triangle. So we are familiar with the basic mathematical shapes and their areas. Now we have an hexagon. Hexagon is a bit complicated figure. So now if I ask you what is the area of this hexagon, can you find what is the area of a hexagon? I am not asking you to find the specific formula for the area of a hexagon. Just use your understanding from my previous examples. I showed you that the area of a rectangle, area of a square, area of a triangle, and you can use this elementary knowledge of areas of basic shapes to find the area of a hexagon. And do you know how? Let me show you. I can draw a perpendicular here and one perpendicular here. So I have divided this hexagon into three basic shapes, two triangles and one square. And I already know how to find the area of a triangle and a square, and I can find their relevant areas, and then I will add those areas to find the area of this whole hexagon. So this is how I will do that. So I will calculate area of a triangle, then area of a square, then area of this triangle. Of course, these two triangles are same, so I just need to find the area of one triangle, and I will multiply it with 2. I will get area of two triangles, then I will find the area of this square, and I can add them up to get the area of a hexagon. So you know, if I get a bit complicated shape, I can use basic formulas of mathematical shapes to find the area of a complicated shape, but just by adding them up, like in this case situation. Now my next question is, can you find the area of this shape? You know, this is an irregular shape, and it's not easy to find the area of this shape, right? You must be having some difficulty. So let's try to get or try to build up some knowledge. How can we find the area of a triangle? So one idea could be, actually it is not my idea, this idea has been discovered long ago, but I will talk like that we are trying to explore this method. So I tell you a method that how can we find the area of this shape. And the idea is, I can I can divide this shape into different rectangles like this. And of course, I know what is the area of a rectangle. And if I add the areas of these rectangles, I can find the area of this shape, right? And of course, I know this will not be a perfect area of the shape, you know, because this area is left. So my calculated area will, and you see here, some extra area is included. Because if I find the area of this triangle, these, and these, then of course that area may be an estimate of the area of the actual shape, but it is not a perfect area, because some area is left, and here if you see, some unnecessary area is included in my calculations. So this is not a good way to find the area of this shape by inserting number of rectangles, and then I find area of those rectangles, because I know how to find the area of a rectangle, and then add the area of those rectangles to estimate the area of this actual shape. By the way, let me clarify one more thing, that when I suggest, it has been suggested and done, but I am talking like that, that when I say that I put here now 5 rectangles, so there are certain conditions of this method, so I want to clarify that one. One limit is that the width of every rectangle is same, and I can call it h. So the width of this rectangle is also h, mean the length from this end to this end. Similarly, this is also h, because that is an important limitation of the method I am going to explore. So they have same width. So whatever width you choose, it should be the same for all the rectangles. You can change this width. Mean how many rectangles you decide to put into the shape, it's up to you, but always remember you have to keep h same for all the rectangles. You may decide to put 10 rectangles, and you may want to stuff maybe 10 rectangles into this shape. It's okay, no problem, but the only limit is keep this h same for all the rectangles. You may even stuff 100 rectangles, I don't mind that, but just keep this width same. And then you may ask me that, okay, we know how to find the area of a rectangle. Of course, we need to find the width, and then we also need to find the height or the length of the rectangle, because then I will multiply. If I want to find the area of the first rectangle, I will find it L cross H, length into width. Here width is H. And then, of course, length is, in some cases it may be the same, but in other cases length may be different. So I have to calculate the area of each individual rectangle. So whatever length of this, so I think I should call it L1, L1. So here I will call L2, H. H is same, so I don't need to. So here is the length of this rectangle is L2, and I can say the length of this rectangle is L3. Here is L4 and L5. When whatever is the length of the corresponding rectangle. So I can calculate the total area of this shape like L3H plus L4H plus L5H, right? I can find. So now I have said that I can fix the width of the rectangle, and it should be the same for all the rectangles. But you may ask me, how can we find the length L1? How can we find the length of these rectangles? They have different lengths, and how will I find them? There is also another limitation. Let me explain it here. That when you want to put a rectangle in this shape, of course you have to keep the width, which is represented by h here. It should be the same for everyone. And then you can increase the length of rectangle until one of its end touches the upper line, this curvy line at the top. It should touch any one end of the rectangle. For example, here I have chosen the left ends. So whatever is the left point, it is touching the upper line. So see the second, it is also touching this line here. Then the third one is touching the line here, the top line. For the fourth, so I chose that when I will put the rectangles inside this shape, I will extend the length of the rectangle so that its left corner, in this case upper left corner, will touch the upper curve. So you see, when I put the fourth rectangle, I I change the height of this rectangle until it touches the curve, its upper left corner touches the curve, and I don't care about the right. Of course, it has to rise at the same height, but I have to decide how will I put the rectangles inside this shape. You may decide to put the right upper right corner, that when I will choose to put the rectangle inside this shape, I will extend the height until the upper right corner touches the upper curve. It's up to you, but I will explain it later that in sometimes it matters and in sometimes it doesn't matter. So it's up to you. But whatever you choose, just use the same scheme. I mean, if you want to uh, choose the upper right corner to touch the curve at the top, then do it for all the other rectangles. So whatever you choose, it should be the same for all the rectangles in the problem. And you also say that because of the limitation that we have to put the same width edge. So you see here I am getting some extra area in my calculation. It will also add some error into my calculated area. So let's see how can we find the length of this rectangle, or we can call height of this rectangle, because in order to calculate the areas of these rectangles we need a length and width. So let's see how can we do that. Suppose I have a function here, and this function is y equals x squared. It is actually a parabola. It is a very common shape we usually come across in the geometry. So here I have this function. So sometimes we represent a function with only y, or sometimes we can write f of x equals x squared or y equals x squared. And here I am showing you the graph of this function y equals x squared. If I have this function and now I want to calculate the height of this line, I have this green line and I want to calculate what is the height of this line. So if I keep it here and I put it in such a way that it just fits in such a way that one end is touching the horizontal scale, whatever scale it is, and then its upper end is touching the function. So this is a line which is straight up, it's a vertical line, and on the below it is touching the horizontal axis, and the top end is just touching the function. Now I can find the height of this line. And how can I calculate the length or height of this line? It's easy. I will just draw a line from this end to this end, and it is touching the 4. So I can say that the length of this line is 4, because I can see this length is equal to the length of this given vertical line. So you see, if I have a vertical line and it is touching the function somewhere, its tip is just touching the function, then I can find the length of this line by projecting a line to the vertical axis, and of course this length is same to this length. Or alternatively, I can find the length of this line from the function. For example, y equals x squared. So now I need to find the position on the x-axis. It is touching at 2, right? When whatever is the horizontal scale. This line is at 2. So I can put 2 squared. It's 4, you see. So I can either use this formula or I can do it graphically, a vertical line. So now you know how to calculate the length of a rectangle here, because I told you you can put the rectangles inside this shape, and I told you to make sure that any one corner, whatever you choose, but do it for all the rectangles. So here I chose the left corner to touch the upper line. Why? it must touch the upper line. At least one corner should touch the upper line, because this line is actually a function. It is a function, because you see, like I have a function here and it is like a parabola. So because this is a function, so it is also representing a function. And in order to find the area below this function, if you understand that actually we are finding the area below this curve. Rest of the shape is just straightforward. The top one is the shape which only matters, because then we need to find the area under this whole curve. And once we know the function, the function of this curve, it's easy to find the height of this rectangle because it is touching. And if the vertical line is touching, we can find the length of this line by putting the horizontal scale value wherever it is on the horizontal scale. We will put this value into the function, and that function will give us the vertical value. So you see, how can we find the length of this rectangle? And width is, of course, is constant for every rectangle. So let's go next. This is a very rough estimate, and you know that there is a lot of error. For example, here we are just leaving this area, and some unnecessary area is just included in the calculation. This is not a good estimate after all. So one method could be that I increase the number of rectangles. I told you I can increase the number of rectangles as long as I keep the width of every rectangle the same. So width should be the same. For example, whatever I choose, it should be h. Of course, in this case, this h is smaller than the previous case here. Here h was larger, but it was same for all the rectangles in this problem. So here, whatever I choose, it is same for all the rectangles. You see, now my estimation is getting better and better. If I calculate the area of this rectangle, and now you know how can I find this length L. Once I know the function of this curve at the top, I can find this length very easily, because I will plug in this value from the horizontal scale into, suppose just say that this is the f of x, the value of this function at the top, this curve, whatever it is. So once I know the function, I will put this value from the horizontal scale into this function, and I will get the length L of the corresponding rectangle. And now you see that my accuracy is getting better and better. But still you see there is some area which is left here and here, and some unnecessary area is included. This is not a perfect calculation of the area below the curve. So how can I increase the accuracy of my method? So let me get into the real detail, and this will finalize the concept of integration. So I will get the perfect area under below this curve at the top if I keep on increasing the number of rectangles, and it's up to me. And when the number of these rectangles becomes infinite, I will get complete or perfect area below this curve. So let's get into the calculation. So here I have a function, this curve at the top. So it is just a function f of x. I don't know exactly the value of this function, but we are just going into the analysis because this is just a hypothetical function. And so I have here the first rectangle, second, third, fourth. So I just keep going that up to n rectangles. Because later on I can do the analysis. I can put conditions on the n. I can put n as 10, 20, 50, or even just infinity. So here I have the function. So I decide that width of every rectangle is h. So for the first it is h, and the boundaries I have put that this function starts at the horizontal axis, that a starting point is a, and where the function ends, here, so I just put a straight line, and here the last point is B, because I have to divide this interval A to B between different rectangles, right? And each rectangle has width h, and next rectangle it has also width h. Width is same, but this value will change like that because the first point is A. Now the next point here, mean where I will get the width of this line. You know that when I want to calculate the area of rectangle, I need width, which is given here, but I also need the length of this side. Of course these two sides are equal, but I chose the left side because it is touching the curve here. And if I want to get this length, I need to get this point on the horizontal scale, this point, because I will put this point into this function here, and this function will give me the length of this line, and I have already shown it to you. So the next point, so I need to track the points of these, only the left points, right? Because I chose that only the left side is touching. I don't care about the right if it is touching or not, but I am using only the convention that I will increase the length of this rectangle until the upper left corner touches the function, because then it will give me the height of this rectangle if I know the function of the curve at the top. Of course, and for the next, when for the third rectangle, this side is located at a plus 2h. So you know that here is a, then 1, 2, and this is, so now there are two heights, so it should be a plus 2h. For the fourth, it will be a plus 3h. Mean the point where the left side of the rectangle is touching the horizontal scale. That point is a plus 3h, right? And in this way, I will keep going. And this is the nth rectangle. So the left point will be a plus n minus 1 times hb. You know that, for example, here this is the fourth rectangle, but its left length is located at a plus 3h. It's always less than the number of rectangle. The number of rectangle is 4, but this point is located because I am taking the left vertical lines of the rectangle, not the right ones. So here this is located at a plus 3h. You see, a plus 3h is the same a plus n minus 1 times of h, and this is the fourth rectangle. So a plus 4 minus 1 times of h, a plus 3h. Here is there. So similarly for the nth rectangle, this is left vertical line which is touching the function here. This will be located at a plus n minus 1 times of h, because this is I want to represent everything into equations and variables, so that then I can put the conditions on top of them. So this is the location of this one. So now let's calculate the area of these rectangles according to our method. So here the total area, let me scroll down. So here I have the total area below this curve at the top. You know that it is actually the same. Whatever curve is at the top, we are finding the area below this curve. And so the total area equals sum of all individual rectangles here. So I chosen like n number of rectangles to put in the below this curve to fill the space below the curve. Now the next step, then total area should be equal to area of rectangle 1. Then of course I will add plus area of rectangle 2, which is here. Then of course area of rectangle 3 here, and in this way it will keep going that until I arrive area of rectangle n. The last one is n. So area of rectangle n. So this is how I will calculate the area, right? The next, now I will use the formulas. So total area will be equal to width multiplied by length of rectangle 1. The subscript is showing that is the number of the rectangle. So for the first one, I need to find the width and then length. Of course, this is the area of the rectangle, plus width and length of rectangle 2, plus width and length multiplied by length of rectangle 3. Similarly, I will keep going, and for the last one, of course, I need to find the width of the last rectangle, and the length of the nth rectangle, or the last rectangle in this case. Now I will put the values here. So you see, total area. Now this is the area of first rectangle. So you see, h is the width, and of course it will be the same for all the rectangles. And then if I want to find that this length, the length of left line, because according to my convention I will only take the length of the of course it is equal to the right length, but according to the convention I am choosing to take the left vertical length of this rectangle A, and of course it is equal to f times of A, because this line is located on the horizontal axis at point A. This is just the arbitrary point I have chosen, A. And you know that if this line is touching the curve at the top, and if I know the function of that curve f of x, I will just put this value A into this x, and then this function will give me the length of this line, right? I have already shown you this, that if a line is touching a function, and if you know the location of that line on the horizontal axis, it will give me, if I put this value on the horizontal axis into the function will give me the length, vertical length of this line. So you see here, this is what I am doing. Now the total area of first rectangle is h times f of A. So whatever is the location of this line, I will put this value into the function, and function will return me the length of that line. So that is why for the second rectangle here, h times f of A plus h, because for the second rectangle its left line is located at A plus h, and when this A plus h will go into this function in the place of x, this function will give me the length of this line. So I am getting the length of the second rectangle, and then I will multiply this length with the width, which is h of course, plus h and A plus 2h, you see, because for the third rectangle it is the left line, its left side is located at A plus 2h, and when I plug this A plus 2h value into the function will give me the length of that line. So h times A plus 2h, this is the area of third rectangle, and in this way I will keep going that, and then I will arrive at the nth, and the left side of nth rectangle is located at A plus n minus 1h, and I will insert this value into this function in place of x, and function will give me the length of this line, and that's why here I have the area of nth rectangle, h times f of A plus n minus 1h. This sum is called as Riemann's sum, a very brilliant scientist who discovered this estimation method, because we are estimating, right, the area under the curve by this method. We just put rectangles according to certain conditions. Of course we keep width of the rectangle same, and then this is how we find the length of the rectangles, by using the function of the curve at top of them. So this is called Riemann's sum, and I, of course, because h is same in each value h, so I can take h as common, and then I can put all the functions f of A plus h, f of A plus 2h. These are the lengths of the left sides of all the rectangles under this curve. So you see, these f of A plus h, f of A plus 2h, these are the vertical lengths of these rectangles, and this is length of the left side of these rectangles. Of course left and right sides are equal, you don't have to worry about that, but this fact is important, and I will explain it later, that it matters if you choose the left side or right side, and it matters only in calculating the area below this curve. It will affect the accuracy, and I will explain it in very clear detail later, but for now, so these are the lengths, addition of, if you add the lengths, because width is same for all of them, so I just took h as common. Now here comes what is integration. So if we put a limitation that when h becomes 0, or in other case I can say, if I decide to insert unlimited number of rectangles below this curve. If I put a condition, that's why I use this methodology, I use this variable, so that now I can put conditions mathematically. So I say that the number of rectangles are infinite. So when number of rectangles are infinite, if you put more and more rectangles, you observe that this height, this width h will keep on decreasing, right? Because if you remember from the initial slide, that here the number of rectangles are only 5. So you see this width is too much. And then I chose the number of rectangles maybe 13. So you see the height h is decreasing. And now if I put the condition that the n approaches infinity, this height h will of course become 0 because it is decreasing. If I am increasing the number of rectangles below the curve, the height is decreasing. So if I keep on increasing n, h will keep on decreasing, and a limit will come when h becomes infinity. H, the width of each rectangle, will become 0. And of course, rest is the same. It is Riemann's sum. This is how we calculate. And if I put this condition, I will get the perfect area without any error or without any misestimation. So that total perfect area is actually the integration in which you have this function f of x, and according to my definition or the process, you know that this is actually that function, and then this is the width of rectangles here h, and dhf is just showing that a partial width, and a and b is the limitation, the initial and final point, because you want to calculate the area, a definite area below this curve. If you know the definite points between which you want to find the area, of course this is the limit that the function starts, that calculate the area below the curve from the point A and or between the points A and B, find the area below that curve. And what is that curve? This is f of x, this is the equation of that curve, and d of h, of course it's showing the width of rectangle you are doing, and this width, you know that after putting these two conditions it becomes integration. And whenever you want to evaluate an integral like this, you are actually doing this whole process. This whole process is encapsulated into this integration. So when you want to solve an integral, whatever integral it is, this whole process which I have explained to you right now is just included in this integral. So when you want to calculate the find the integral of a function, any function, you are actually doing everything in that integral. So the only difference is Riemann's sum, and integral is this limit. When you put this limit, that and when n becomes infinite, h becomes 0, and when you impose this limit onto the Riemann's sum, you get this integration. And next we will solve some problems related to integration, and you already know that there are two integrals. We call them definite integrals. If you are given the limits, the initial and final limits between which you want to find the area, the area below this function, and this is the width of those rectangles you want to choose. And we have indefinite integrals in which no limit is given, so you just need to evaluate this integral and you don't need to put the limits. Of course, without limits you will only get a function, not a specific value. And we have different formulas to calculate the integrals. You see, if you have a constant value, the integral is just x plus constant of integration. If you have a value with a power, then this is how you will calculate the integral of that function. And once again, whenever you calculate, for example here, if you have a certain function, x of n is the function and dx is actually the width of those rectangles which you had in Riemann's sum, and of course there is a limit. So once you get this the process of solving the integral from this to this, all of that process is just done in blink of an eye. So just keep in your mind that when you are solving the integral, actually that whole process is encapsulated into this integral, and when you solve it, that whole process is just done and you find the perfect area below that curve. And that is actually my definition. Later on you will see that this is not the only way to picturize integration, because integrals have a vast applications in science, engineering, everywhere, and it doesn't mean that it is always only the area below some curve, because that area may represent a lot of other quantities, physical quantities, and not only the geometric area of some shape below that. So now let's solve an integral. Here I have an integral sine of x dx, and we are also given the limits that start from calculate the area below this function between 0 and pi by 2 angle, because sine of x is of course can go indefinitely along right and left direction, but we want to find the area only between these 2 points from 0 to pi by 2. And you know, function is sine of x, and this is of course, you know, that increment of the rectangles below this function. So according to our definition, this question basically is saying that find this area, the yellow area I have highlighted. This is the function sine of x. Of course, it is going to the left and right indefinitely. But because it is given that only find the area between 0 and pi by 2. So here I have 0 and here is pi by 2. So we only need to find the area, this yellow highlighted area, and not any other area. And of course, function is given y is equal to sine of x. So you are given this function, and then here is the width of those rectangles which we chose here, and those rectangles are just unlimited here. So that will be d of x, the width of here. So everything is just included. You don't need to do that. Just solve this integral and all of that process will be done automatically. So sine of x dx will be equal to minus cosine of x. Let me remind you from the formulas. Here I have that if you have an integral in which you have a sine function, only isolated sine functions, then it is equal to negative cosine of x. So if I use this formula, I know that this sine of x is equal to negative cosine of x, and the limits 0 to pi by 2 will come here after solving this integral. And yes, in blink of the eye, all of that process is just done, and you will get the perfect area without any error. We are solving it analytically. It means there is no error, no leftover area or some unnecessary area, no, never. So here we have negative cosine of x, and the way we put these limits, first put the upper limit, so negative sign is outside. I will put cosine of pi by 2, upper limit will come first, then you will put in negative sign, and then cosine of 0, you will put the lower limit at the end, and after solving the area is 1. So this yellow area is 1 between 0 and pi by 2 of this function sine of x, and everything is just done. This is the perfect area without any error. And now it's your turn. Can you try to evaluate the following if you have cosine of x and dx, and if you want to find 0 to pi by 2, then the area below this function cosine of x between point 0 and pi by 2, find the area of this function cosine of x. And don't worry, you can always see the table of values. Cosine of x equals sine of x. So I think it should not be very difficult. You can just solve it, and you may try to have the graph of this function and visualize that what is actually that area. Find the area of a rectangle using integration. So we have a rectangle here, length is a, width is b. Of course, we know the area of this rectangle from our geometric formulas. It is a multiplied by b, that is the area. But I want to use integration, because in this exercise you will see like integration is not always the choice sometimes. Because for using the integration, even I have the question, because this is not a right question in fact, that you cannot ask someone to find the area of a rectangle using integration. Why? Because for integration, at least you are supposed to give me the function of the upper curve, whatever it is. I mean, at least give me the equation of this upper line. That's it. Once you give me the equation of this curve, whether it is a straight line or curve, whatever, but at least give me the equation of this one, f of x. Then I can use integration very easily. That is the least. And then you can give me these limits if you want. But that's up to you. Because if you don't give me the limit, I will just calculate it using indefinite integrals. Because it is not given, so let me try how can I find the equation of this straight line, because this is just a straight line, it is easy to find its function. And in the next step, this is what I will do that, because for integration you need the function. That is very important thing, because in the integration you know that we find the area under this curve, and to find the area under that curve we just assume some rectangles, and then width of that rectangle will be dx here. And to find the length of this rectangle, at least one side, length of one side, we need to find the position of that side of the rectangle here. And once we find that position, we will insert that coordinate here in f of x to find the length of that rectangle, whatever it is. So let's find the function first, and then we will use integration to solve the question. So to find the function of that line, here I have that line, that vertical line only, because in integration you already know we only care about the upper line or the function or curve, whatever it is. And then we will just find the area below that line. So first I need to find the equation of this line. And what should be the equation of that line? Let me see the function. So here I have this line, the length of this line is a, and the width of this rectangle is b. So it means this line should be at certain height at b, because this length is b, right? So if I have this coordinate plane, that Cartesian plane, I can put it somewhere here, right? So here the point is b, because this width of that rectangle was b. See here, this width is b. So I place this line at some Cartesian plane, and then this point is b from the origin, and this is where the point where this line is ending. This point is a, because according to the given shape, this horizontal length in this case is a. So I just chose that this point is a, and I place this line along the vertical axis at a height b, so that it will become a rectangle of the same size. And placing this horizontal line in this Cartesian plane will help us to find the equation or the function of this line, and that function f of x equals b, or I can also write it like y equals b, because you see it is at point b. This is of course origin, so it should be from 0 to b, and this one is 0 to a. The length, and it is just a rectangle, but if I want to find the area below this line, which is actually the area of that rectangle, in other words, I need to find the equation of this line. And now I got the equation of this line. It is y equals b, or f of x equals b. And of course this interval is from 0 to a. So I got the limits of integration. I want to find the area below this line between point 0 and a. In our case, of course, that is the area of that rectangle. So let me put everything in integration form. So I have here the integration, the interval, the area, I want to calculate between 0 and a, and here I have f of x and d of x. D of x is just the width of rectangles which I want to assume below this curve, and then the number of those rectangles become infinite and length become the width h becomes 0, and I get the maximum area, and that is done by solving this integral. And now it's time to solve this integral. So 0 to a, and function f of x is actually b, and then I have dx, because the horizontal axis is x-axis. I can name it like x-axis, this is y-axis, just to keep everything in context. And now it's time to solve this integral. Once we solve this integral, we will get the area of the rectangle. So let me see the table, the integration, the value, the table of integration. So if we have a constant value, whatever it is, 1 2 5 8, and then we have dx, it says that it should be equal to x plus c. C is just constant of integration, which we will ignore right now. So it's equal to x, right? So let me go back to the equation. So here remember that b is actually constant. If you have any constant as a function in the integral, that table says that it should be equal to x, and now I will put the values 0 to a, and then b will come here. So just remember that if you have a constant, for example 5 dx, the integral will be 5x, the solution, because in this table of values it assumes that the constant is 1. So if it is 1, then you only see the x value. But if it is, for example 5, then of course it will be 5x, like this. So because this b is constant, so b will also b will come appear along with x and the limits of integration 0 to a. And the way we impose these limits of integration is that b is constant, so it will remain outside, and these limits of integration will go into the x value, which is the variable here. And first we will put the upper limit, so instead of x I will put a, then I put a negative sign, then the lower limit will come 0, and here is b into a, or I can write it a multiplied by b. This is the area of the rectangle we were given in this situation. So you see, I found exact same answer which you would find from your previous knowledge of area of a rectangle. You know that area of a rectangle is a cross b, and this is what I found from integration. So you see that it's a very fantastic tool to find the perfect area of any curve. This was an oversimplified problem, and you will never want to use integration to find the area of a rectangle, because you already know the area of a rectangle from your classical formulas from geometry. So that is the problem, because that is the point I want to make, that integration is not always an easy tool to find the area of any shape. There may be many. The first problem with the integration is that you need to have the function, and the process is a bit lengthy. So whenever possible, always use the classical formulas to find the areas of basic shapes, for example triangles, rectangles, squares, hexagon, whatever, as much as possible. And once you don't have any choice, for example if you have a curve like that or a very complicated, then of course and even for that you need to have the function of that curve below which you want to find the area. And you know that it's not easy to find the equation of that curve, you see, because here it was just a straight line. That is why I was able to find the area, find the equation of that line myself. But if the curve is like this, even it's not easy for me to find the equation of this function unless it is given. So whenever you are given a function and then a limits, now what is the reason of those limits, that you will arrive at the fixed solution by putting the limits. But if you don't put the limits, you would just stop here at bx, that is would be the result of indefinite integral. So just if you assume that no limits were given, so your answer would just stop here, bx. So you have this bx, and whenever you want to find the exact answer, you could get limits. For example, if I have a rectangle, I give you that I have a rectangle, and this width is 2 and this is 3. So you will say, yes, okay, now b is equal to 2 and a is equal to 3, the limits of integration. So now you will write 2x and the limits of integration 0 to 3, and you know that this will answer to 6. So once you have the answer of indefinite integral, it's easy because you can use it anytime by imposing the limits. If next time I give you a rectangle, for example, here it is 5 and suppose this one is 15, you can just put these limits into the answer you got from indefinite integral, and then you can get the exact answer whenever you want. That is the only difference between definite and indefinite integral. Other than that, they are same. Now we have another question. Find the area of rectangle using integration. It's actually the same problem. Before I used b and a, but now we have definite numbers. So let me do it quickly. So if we want to use the integration, of course, you know that I need to have the equation of this line at least, because below which I will find the area. So once again, I will try to find the equation of this line myself. So here I have a Cartesian plane. I have some values. Here is x-axis, y-axis. And here I have the line, the upper line that with the same weights. I will put it at 3. You know that why I'm putting it at 3. Because then it becomes a equal, the same rectangle like it is given here, 3 and 5. So I put this line at the scale above 3 units. So here you see it started from 0 and I put it at 3, and it ends at 5, you see, because length of the line is same, so horizontal has 5 units here, so it stopped at 5. And this is how I will find the equation of this line. So can you help me, what is the equation of this line? It's easy to find, right? Because it is at 3 and the value of y is always 3 along this line. So equation of this line is y equals 3, or f of x equals 3, and the limits of integration are 0 and of course 5. So if I want to put it in integration form, the limits of integration are from 0 to 5, and then f of x dx, you know what are these values, and of course I know the value of the function 0 to 5, and the equation of the line is y equals 3, or f of x equals 3. So here is 3 dx, and you know that this is a constant. If you get a constant, the table of integration says that you will put x along with the constant. So let me do it here. So the solution of this integral is 3x, and then I will put these limits 0 to 5, you see. So because 3 is constant, so it will remain outside, and I will put these limits into the x. So first time I will put the upper limit, so it is 5 minus 0, and you see it is 15. Yes, the area of this rectangle is 15. You know it is multiplication of width and length. 5 multiplied by 3 is 15. That is what I got, the same answer, but you know it was a bit complicated. First I needed to have the function and then put limits of integration. So integration is not always the tool of choice, but it is very useful for complicated functions. When you are given this function is very complicated, of course you will face a lot of complicated questions. These problems are oversimplified. You will never see these problems in your exam, of course, and these functions are very complicated, and you will go through different techniques how to solve this integral analytically. So I just use integration to find the area of a rectangle like this, and the area was a 15 unit squared. Now I will use integration to find the area of this rectangle, but using a slightly different method. And this method is very important. It will give you the perspective how can we calculate the area. You remember in the first method, I took this upper line, right? This equal length line, I put it in the Cartesian plane to find the equation of this line, and then I found the area below this line in my orientation. Remember, it was in a Cartesian plane like this, and it makes the same rectangle with same dimensions, and I found the area below this line, right, according to this orientation. Now what I will do, I will take this line, this smaller width line of this rectangle. So here I have this Cartesian plane, x-axis, y-axis. Here is the vertical line of same width, and I will put it at, let me see, it is, the length is 5 units, so I will just go at 5, and I can put it there, right? And of course, because the length of this line should be 3 here, so I have the same line here, and I put it like this. Of course, it still makes a the same rectangle, right? But now I will find the equation of this line. So equation of this, what will be the equation of this line? Can you tell me the equation of this line? The equation of this line will be, now x equals 5. So it's x equals 5. So now I have this line. I want to find the area onto the left side of this equation. So you see, if I draw a straight line here, it is still the same rectangle. You see, it is still the same rectangle, but now I have the equation of this vertical line at 5. I have equation of, and I want to find the area onto the left side of this line. Of course, that area will be the same, right? Because it doesn't matter. How do I calculate the area? So it means now I mean, according to our definition, that I will assume unlimited number of rectangles like this, and then width of this rectangle will be dy. Of course, because of the convention now, because they are on the y-axis, so this width I can represent the differential width as dy, the small width. Of course, it will become 0 when the number of rectangles are infinite. So now how will I calculate the integration? So I will have the same integration, but now there are some changes. First, the limit of integration is from 0 to 3, right? You see, because now the orientation is reversed. The equation, the function I have is on the x-axis, x equals 5, and now the differential width of the rectangle is on the dy axis, and the limits of integration are always along the width of the rectangle. I mean, how you orient the rectangles, because that limit defines the extent of this function below which you want to find, not below, in this case it is on the left side of this function. So if you want to find, that limit defines. So now we will take this limit, not 0 to 5. Always remember that. So now my integration is from 0 to 3. Now my function is f of y, you see, and the differential width is d of y. So I hope you should be able to understand why I am doing that. Because now is x is equal to 5, and if I have a rectangle here, and if I want to find the length of side of the rectangle, I need to give the value of y here. I mean, that will be the side which is touching on this, and that value will go into this function, and this function will give me the length of that side, right? So that's why I have written here f of y, and now this differential width is along the y-axis. So this y is showing that now the differential width of those rectangles should be along the y-axis. And here we have the function f of y, because we will, in this case we don't need, but if there is a function like this, so we need to give the value of y to get the this length of the side of the rectangle. So let's use this integral. So now the function is x equals 5. So this f of y is 5. So I can write the integral 0 to 3 and it is 5 and dy. And if I want to solve this integral, now it should be 5y. Always remember that if I have a constant, then I will get 5y, because the orientation you see that now is reversed and the limit is 0 to 3, and if 5 is constant, so this limit will just go into the y. So first time it's 3, negative 0, and I got 15. So you see, I still got the same area. Of course it was supposed to be the same, but I used a slightly different scheme of using the integral. I found the equation of this line and I found the area onto the left side of this line and between the points 0 and 3, of course, according to the given shape here. And one last point, that I am using extensively the area of geometric figures to explain the concept of integration. But always remember that integration is a widely used tool and it can represent any quantity and a lot of quantities and a lot of different complex functions, and it is not only limited to the area. So always keep your mind open that this is not that simple. For example, I solved a question in which we have a velocity of a car or a motorcyclist, and then we have the time data, and you see that I have drawn that whole journey on the axis, where vertical axis is velocity and horizontal is just the time, and I use this velocity time graph to find the area of this curve. Of course, I did not use integration because this problem was simple. I divided it into different basic shapes, and then I used the formulas to find the areas, and that area was actually showing the total distance traveled by the motorcyclist in that problem. So you see that area of something is not always just the area. It can represent some other physical quantities. In this case it is showing the distance, and that curve is showing the velocity of a motorcyclist. So keep your mind open that it is not strictly only to geometric shapes, or the purpose of using integration is not only to use a function and then find the area below or left or right or whatever is side to find the area um, of that curve, or it is not limited to that one. I use the concept of the area just to explain the working of integration, that how does it work, and it actually can be used a lot of other functions where it can represent a lot of other quantities, not just a simple geometric area. So when I was talking about putting the rectangles below the curve, I told you that you have the choice. You can decide that you will make a rectangle and you will rise it up until its left corner touches the curve, and you will keep that scheme for all the rectangles in your problem. Here I have an animation and I want to explain that what does it mean and what is the difference. For example, here in this animation I have a curve. This is of course a parabola, and the equation is 0.5 x squared plus 1. This plus 1 means it is shifted up along the y-axis 1 unit up, and I want to calculate the area below this parabola and between the point 0 and 3 along the x-axis. You can see from 0 to 3. So here I have the term upper sum and lower sum. This is what I was talking about. And then I have true area. True area is the integration after putting the condition when we make the number of rectangles unlimited or infinite and the relevant width of rectangle becomes 0. That is the perfect area. You already know that when they will become um, infinite, of course you will get perfect area. So here I have all the three quantities. Here I will have the area upper sum if I choose that all the rectangles the upper right corner will touch the curve. So after calculating the area from that rectangles, then I have lower sum in the area from those rectangles whose upper left corner is touching the curve. So I will take that length because it matters. You see, now I have the number of rectangles equals 1 here. So I will move this slide to change the number of rectangles, and then you will see that the area is improving. So in the middle I have true area, that is the integration which comes out of that is the true area which comes out of the integration, which means after the condition that the number of rectangles are infinite. So you can compare that. Now error is too much. The true area is 7.5 units squared. And if I use the upper sum, mean if I choose a rectangle, of course now I have only one rectangle, and of course the error will be large. So from the upper rectangle, you know that I am getting a lot of area which is not required because I want to calculate the area below this curve and between the point 0 and 3. And you see that it is the upper sum is 16.5 units squared. It's a large error. And similarly, if when I choose the lower sum, mean upper left corner of the rectangle should touch the function, because then I can get this length to find the area of this rectangle. So this 3 unit squared is, of course, you can see easily that this is actually the area of this rectangle, because I have only one rectangle, so error is large. And area of this rectangle is, of course, length is here is 3, and here you can see the width is 1, so the area is 3 unit squared, and the area of the upper sum is 16.5. I have a lot of errors. So now let's see if I increase the number of rectangles. So now the number of rectangles are 2. So you can see that now error is decreasing. You see, from the lower sum in the red rectangles, for which the limit is for which the scheme is that the upper left corner will touch the function, and even for the first one is same. You see, this scheme, and then for the other scheme, the upper sum, it means that I will choose to touch the upper right corner with the function so that I can get this length, and of course width depends on the number of rectangles, of course. So that interval will be divided between those two rectangles according to the number of rectangles. And here I have the second rectangle is upper right corner is also touching the function. So you see, it's not always the same. Error is different. For example, sometimes lower sum is better for your function, sometimes upper sum is better. But this is only for computational integration, not for analytical solution of the integration. When you solve the integration, always remember that the number of rectangles are unlimited and infinite, and you get perfect area, so there is no question. This is only when you want to calculate the Riemann's sum. You know, the Riemann sum will only calculate the area from these rectangles, not the integration. Integration is next step to the Riemann sum. In the Riemann, it puts a condition that the number of rectangles are infinite, and then that is the integration. So here you get the result of integration in the middle, which is saying a true area is 7.5, and then the lower sum, the area is 4.6, and upper sum, you see the error is different for both. So sometimes it's different. If you don't want to solve the integration, sometimes you can calculate the area from Riemann's sum without putting those conditions. So I am just showing the function that it matters if you choose the upper right corner to touch or the lower upper left corner to touch the curve, and the relevant errors are different. It depends on the shape of the curve, actually, that what is the shape of the curve. So maybe for one curve the upper sum is better, and for other lower sum is better, and of course the true area is the best if you can solve the integral of that function or problem. So as you can see, now I am increasing the number of rectangles. So you see that as I am increasing the number of rectangles, you see the area from the lower sum and upper sum is getting closer to the true units. And when they become infinite, of course, they will become equal. So you see 7.3, 7.5, 7.6. And now even the relevant errors, even these values are still different, you see. From the upper sum, mean when you choose the rectangle to touch the upper right corner, is different than the when you choose the rectangles if they want to touch the upper left corner to with the function. You see the values are still different, and it matters sometimes if you are calculating. So now if I keep on increasing, you will see that now area is of almost equal. You see, even from the lower sum it's 7.4, in from the upper it's 7.567. The error is very small. Of course it will never be equal. You get only true area after solving the integral analytically. It means the method you will learn in your textbook, you are actually solving them analytically. And the upper sum and lower sum is actually the area from 100 rectangles only. So of course it is not infinite. So from the 100, it is only the area from the Riemann sum without the condition that this n is actually infinity, which is the true area, 7.5. But it is very much closer. So now you can feel like how the integration works, and those limits also matters, upper sum, lower sum, and of course true area is the best. When you are calculating the true area, when you are calculating the integration, you don't have to worry about upper or lower corner. That is only relevant to the Riemann sum when you want to compute or estimate the area without that condition, because sometimes it happens that in the advanced applications in science and technology, you have an integral which you can't solve it analytically when using your techniques you are learning in your textbook. Of course you don't have any problem in your textbook which cannot be solved analytically, but in the advanced application it happens. So then you will use your computer to increase the number of rectangles, because computers can do that, and then you can calculate the area of those rectangles to get a good estimate with the true area. I hope you understand the integration, its applications, and of course there are a lot of techniques how to solve the integral. That is the actual point. And when you want to solve those questions, I hope you will enjoy solving those questions because you know what is actually an integration.